I'm Will Darner, and this is my final project for ECE 430. For my final project, I decided to model a pacemaker as a cyber-physical system. So some quick background on a pacemaker. It detects abnormal heartbeats, which are normally called arrhythmias, and it usually has two lead wires, one on the atrium and one on the ventricle, which are two out of the four chambers of the heart. And what it does is it paces either one or both of the chambers with a shock of 0.5 to 5 volts, depending on the detected arrhythmia. So a few of the common arrhythmias are bradycardia, which is a slow but consistent pulse, atrioventricular block, or AV block for short, which is a regular pulse that has abnormally spaced beats. And there's atrial fibrillation, which is also shortened as AFib, which is where the upper chamber beats chaotically out of sync. So that's where you get varying widths between pulses. And other types of arrhythmias, such as tachycardias, which are rapid heart rates, usually are not treated by a pacemaker because it's hard to determine them from, say, exercising paces of the heart rate. So to start out this project, I decided to model the heart rate in MATLAB. And because it's very difficult to get actual ECG data to be replicated and reproduced quickly in a model, I decided to instead use a Gaussian pulse with the 1D wave equation, and that gave me a lot more speed on my model and let me simulate it in real time for a heart rate instead of something being a lot slower with an ECG approximation. And the arrhythmias, I was able to use the same Gaussian pulse, but just alter the period between pulses to get the desired output for that. So here's some of the code for my MATLAB. Basically, I have my main function, which is the one on the left, and what that does is I have a solved 1D wave equation update equation, which is what I use to, at each time step, update it with center difference method. So I have the current point, the previous point, and the point ahead of time that will help me calculate where the wave needs to be. And then at the bottom of the left one, you can see that I have the input pulse as an exponential, which is modeling the Gaussian exponential. And then on the right here, I have this big rhythm function. And what this does is determines which rhythm I'm choosing at any given time. So at first I have normal, which has a period of 1, because that's the baseline of 60 BPM. And then bradycardia, which I'm modeling as 30 BPM. So I change the period to 2, meaning that it's going to only beat half as much. And then AV block, I have a array of zeros initially, and then what I do is set it to a regular period and remove every third beat to show the AV blockage. And for AFib, since it's chaotically random, what I do is I take a beat, and then for the period between the two, I choose 0.45 seconds plus 0.8 times the rand function to get that, because the rand function chooses a random value between 0 and 1, and that's too big for what I'm looking for. So I use 0.8 times that. And so what that ends up doing is that function can output anything between 0.45 and 1.25 as a space for the period. So here is the output of everything. You can see the top left is the normal pulse, top right is the AV block, bottom left is the AFib, and bottom right is bradycardia. And since they're all sunk up to the same time, you can see exactly how they interact with each other. So then to work on the rest of the project, I decided to model the heart rate in Python. The reason why I chose Python over MATLAB is because I want to model it on hardware on an Arduino later, and so it was easier to have those two programs communicate with each other than it was for MATLAB, since MATLAB is usually about modeling data itself once instead of running continuous simulations. And so I decided that the heart can be modeled by repeating the same MATLAB pulses and arrhythmia approximations I made earlier, and that I can send that heart rate data to Arduino as ADC values ranging from 0 to 1023, and then I can have the Arduino return the detected rhythm to my Python console, and have the Python script output the current rhythm to console so the two can compare, and we can see if we actually got the right value. And then I can verify that this works if they both output the same rhythms. So here is some snippets of my Python code. You can see my main loop on the left. What it does at the beginning is I print the arrhythmias in a random order, and I do it in a random order just so that I can see that my Arduino is actually working the way I want it to, and it's not just assuming that I have the same 3 arrhythmias in the same exact order every time. And then what I end up doing is I call the normal heart rate for 10 seconds, and then I call arrhythmia for 10 seconds. And I do this over and over until I go through every simulated arrhythmia. And then on the right here, I have my heart signal, which I made a class, so that instead of having all the variables set up at the beginning in a lot of different areas, I have them all set up under this main class. I also did this because when I was setting up the project initially, I had a lot of different hearts that I wanted to test. Like, I was testing to see if I could get a heart that was only outputting AFib, and I had another one that was only doing AV block, just to see if the Arduino could notice that. And so I have the rhythm set up. I have a next beat time, which will tell you the interval between beats, which can be modified later. I have the number of beats. I have the interval number for afibular, and then I have the active beats, which is then saved into an array of called DQ for later, for when I need to calculate AFib. And then I also have on the left here this run rhythm function, which essentially takes one of the rhythms that's chosen in the order from the beginning of the random array, and it just runs it and outputs what that rhythm actually is. And then it will compare the Arduino output back to it to make sure that it's working properly. And on the right here, I have the sound that's played through the Tesla coil for my demonstration. And this code is generating a 1000 hertz sine wave. Instead of just finding a wave file and downloading it, I wanted to make it in the program so I didn't have to go through all of that. And if I ever want to distribute this, then I don't have to add extra files to it. And so that's what I decided to do for that. And so this is the hardware. I have my laptop USB, which plugs into the Arduino serial connection. And then I have the 5 volts attached to my breadboard, 5 volts. I have the Arduino ground attached to my ground. I have pin 9, which is attached to a 220 ohm limiting resistor, which is then attached to a red LED that goes to ground. Then I have pin 10, which is attached to another 220 ohm limiting resistor. That's attached to a green LED that goes to the breadboard ground. And you can see in the top right corner, that's the image of my actual build. The Arduino model is basically just reading the 10-bit ADC value from Python, which is sampled at 100 hertz. So at 100 times every second, we're grabbing a value from the Python plot. And it has a threshold of 700 to detect the beats from the data. So what I have in my program is that it needs to have read a value below 700 and then read a value above 700, and that will register as a pulse. So this is what we call rising clock data. So I'm only reading the front end of the pulse. I'm not reading the back half of it at all. And I have it set up so that the red LED will blink at each beat to kind of simulate a heart attached to the console. And then I have the interval of beats stored for calculations because the only way to detect certain arrhythmias is, well, actually all arrhythmias in general, is to just find the distance between the pulses, and if it's varying either too far away or if it's just varying in general, then that's how you're going to find the arrhythmia. And then my green LED stays on when the heart is acting normally and will go out when there's being therapy treated. I just put that as sort of a visual demonstration of like this shows when the pacemaker is working versus when something goes off. So you can see in real time how fast it takes to detect this arrhythmia. And then when the arrhythmia is detected, that is then returned to my Python function, which then verifies whether or not I detected the proper arrhythmia. And if the proper arrhythmia is detected, it will send the therapy sound to the Tesla coil. And once that's done, I have a little bit of an interval where the beating count resets and it stops recording data because I want to wait for the heart to regulate, just like what a regular pacemaker would do. So here's some of my Arduino code. I have on the top middle, this is my main loop. So basically I have a function that's read serial input, and that function has me reading the data and also calling various functions to determine what rhythm it is and the calculations for that and what to return. And then also in that main loop, I have update the red LED because the red LED itself, you can see on the left, the function for it is almost acting independent of all the calculations, but it's still running inside the main loop. So what it does is it has a boolean for red light on, and it will only turn off if a heartbeat is not detected. So it'll stay on, and then a beat will happen, it'll turn off, and then next time the beat happens, it'll turn on, and it'll just keep doing that over and over. The bottom left is my green behavior. So I have a evaluation as to whether or not it's equal to the current rhythm, and if the current rhythm is normal, then the green LED will be on, otherwise the green LED will be off. And then on the right here, I have my calculations for classifications of rhythm. I'm counting the distance between beats as milliseconds, so it would be 3, 1700, and 2300. If it's somewhere in between that, then it's going to return bradycardia, which is the slow heart rate one. And then these other two, I have for AV block, I have if the interval count is greater than or equal to 5 and looks like AV block, which is another evaluation I have running in the background as a boolean, which basically that boolean reads whether or not the speed of the heart rate is acting strange or there's missing beats. And so I have those two evaluated with each other, and then that will return AV block if true. And then I have another one for normal, which just reads for the interval count between pulses being greater than or equal to 4. I have my AV block function, which basically evaluates the interval between beats to see if it's steady like a normal pulse, and then looks like AV block, which is a boolean that evaluates whether or not there are any missing beats to the function. And then my normal one is evaluating interval between beats and making sure that that's consistent, and that will then return normal. And for AFib, I again check the interval of the beats, but then I also have this looks irregular boolean, and what this does is it checks to see if the spacing between pulses is completely uneven and chaotic, which matches regular AFib. So there are a few limitations with the current iteration of this model. For instance, simulated pulses are not actually real ECG data. There's a lot of approximations going on, and the Arduino only works with noiseless digital data right now. So if I were to like plug this into an actual ECG, it would not give me the same outputs right now. And I'm also only using a baseline of 60 BPM with no room for error at all. So if there were to be like a very slight delay, that would be normal from a human heart, it would not be registered in this current iteration. And another thing to note for this model is that pulse isn't consistent in everyday life. We have exercising or just anxiety and other things that could just make our heart rate fluctuate, and that's not really being looked at in this model. Bradycardia in my model is only seen at exactly 30 BPM, which just isn't something that happens in real life. Bradycardia can vary a lot, so it's important to know that this model only sees that. And AV block in my model is only seen when every third pulse is missing, but a true AV block could be anything between third pulse missing, every two missing, or just a lot of other things going on. So that's another limitation of this current model. So this is what I would do to improve the model if I had a longer time frame to work on things. I would use an approximation to be closer to a true ECG waveform so that if I were to actually put this on an ECG monitor, I could get a similar output. The next thing I would do to improve the model would be to check for a stable pulse first, and then check if the pulse lies within normal human range. So I would take something, say, like 40 BPM to 120 BPM, and I would be like, okay, this is reasonable from anywhere from a resting heart rate to exercising heart rate. So if it's in this range and it's steady, we're most likely okay. Then I would probably change bradycardia to be a different speed than just 30 BPM. I would go, say, 10 to 35 BPM, and just anywhere consistent in that range would be evaluated as bradycardia. And then for visual demonstration purposes, I would probably change the red LED to be some sort of LCD screen to actually display the waveform and the number for the pulse in real time, because I feel like that'd be a lot better to see than just a red light flashing at varying intervals. The last thing I would do would be to add a variety of different shocks to more accurately match what real pacing looks like. Because right now, what I have is every time, no matter what arrhythmia is detected, there's just one 1000 hertz tone that plays for 1 second. And a real pacemaker would have various ways to treat the different arrhythmias. So this is a quick breakdown on how the demonstration itself is going to work. So I'll look at how the Python script works first, and then I'll move over to the Arduino. So for the Python script, it makes an array of arrhythmias in random order, and then it beats normally for 10 seconds. It runs the first arrhythmia for 10 seconds, and then it will verify if the Arduino detected the proper arrhythmia or not, and if it did detect it, it will send a shock to the Bluetooth Tesla coil. And then the steps 2 and 3 of beating normally and then running arrhythmia will repeat until everything is treated and the simulation completes. On the Arduino side of things, we have it reading data directly from the USB connection to Python as that 10-bit ADC value I mentioned earlier. And then the red light will blink to the received pulse based on the threshold detection that I also explained earlier. And then the green LED will stay lit as long as a normal pulse is detected. And when an arrhythmia is detected, the green LED will turn off and the arrhythmia type is returned to the Python console. So when you look at the console during the demonstration, it'll say Python, and then after that says Python, it will say what Python sent as the rhythm, and then you'll see Arduino, and after Arduino, it will say what Arduino detected, and then you can see the two communicating back and forth with each other. Here's a little demonstration of the final project. I'll start by showing the hardware side of things first, and then during the second run, I'll show you what the console sees, and for the third round, I'll show you both at the same time. So here we go. So it's going to start with a regular rhythm for 10 seconds. Now it's going to switch to AV block. And as soon as it catches it, it will treat it when the green light is out. And now here's what the console is going to do for the second round. So you can see that it's running a normal rhythm. Arduino correctly detected the normal rhythm. And now it's running bradycardia. And once the Arduino detects bradycardia, it will run a shock like that. And I'll go again to the hardware demo so you can see it closer.